Hello and welcome to this lecture. So this is probably the last lecture in the class. We will be talking about doing simulations and comparing error control codes and making plots of error rates versus EB over N0. Okay, so that's the main agenda for this class, for this short lecture here. We've already written decoders for LDPC codes, we've already written decoders for polar codes, the successive cancellation decoder, successive cancellation list decoder. We want to compare all three in a comparable scenario, maybe similar rates and then similar block lengths, and see what happens, what performs better. Now there are a lot of parameters to choose and all that, one can keep exploring the space a lot. I have done it for some typical case. You are welcome to try it for other cases and compare yourself. Okay, so let me show you how I go about doing it so that we are clear on how it's done. Okay, so the first thing is I want to compare. So now for the polar code, I know that the block length, the maximum block length at least, is 1024. So we'll fix that as 1024, and I will want a rate of half. Okay, so now if you do SC decoding, then you don't need CRC, so you can take K to be 512. On the other hand, if you do SC list decoding, successive cancellation list decoding, then you cannot take K equals 512 because you need the CRC, right? So how many ever bits of CRC you have to add, you take. The standard specifies multiple lengths of CRC. What we are going to do is we'll take the message length to be 500, okay, and then the CRC length to be 11. Okay, so 11 is one CRC polynomial which is there in the 5G standard, so we'll pick from there. So you see the total length is 511, and this is sort of comparable, roughly comparable. Now what do we do for LDPC? Now for LDPC, remember there's base graph 1 and base graph 2. Okay. Now if I want rate half with base graph 1, if you remember, the K gets fixed in LDPC, right? K becomes for the base graph 1, it is 22 times Z. Okay. So if that is the case, then for rate half, okay, roughly half I'll put. Okay, so maybe not rate exactly half, or maybe you'll get rate exactly half. You need N to be 44 into Z. Right, so 44Z into, so when I say N, so let me say what 44Z needs to be. The code word bits transmitted equals 44 into Z. Okay, is this, remember Z is the expansion factor, right? So you always have an expansion factor. But there's also this thing about puncturing. So you remember the first two Z bits always get punctured in the LDPC code, so that always happens. So actual number of code word bits will actually be 46 into Z. Okay, so it will not be 44 into Z, 46 into Z, because and then 2Z gets cut off. And then in terms of the parity check matrix also, you have to pay some attention here. Okay, so you have the 22, so actually the overall parity check matrix is 46 by 68, right? That's the base graph 1. Yeah, so that's the base graph 1 here. So you'll have the first 22 rows being the message, and then the remaining 46 being parities. Okay, out of this, the first two are punctured. Okay, the message ends here, and then you'll start getting the parities. And remember, the parities, there'll be this short block which has the double diagonal structure, and then after that it's just diagonal, right? Oops, I didn't get this right. Diagonal right up to this. Okay, so now what is the meaning of saying number of code word bits is 46 into Z? Here is where the rate matching comes in. I have 22Z here, I need totally 46 into Z. So how many more will I take? I'll take 24Z more. So how many parities will I take for rate half? For rate half, I will take 24 parities. So I'll stop there. Okay. So when you stop there, remember there are 24 parities that you got here. Beyond that, you're puncturing, right? So you're not transmitting those code words beyond the 44. So your parity check matrix sort of shrinks. Okay. So you have to use only this part of the parity check matrix for decoding. Okay, so used for decoding. So this is something that we saw before in one of the lectures on how to adapt the rate matching to the LDPC codes. Okay, so this is just some numbers. Remember, even though you have 46Z, the first 2Z gets punctured, only 44Z is transmitted, so you have a rate of half. That's number one. The next thing is I want a block length around 1024, right? So this needs to be around 1024. Okay, so that also sort of fixes Z. Okay, so from here if you see the value of Z will get fixed around what is 1024 divided by 44, it's I think roughly around 24. Okay, so this gives you a Z of around 24. Okay, and if you go now look at the list of expansion factors possible in the LDPC code, you can do that. If you see the base matrix, the list of base matrices, you see 24 occurs here. Okay, so that's the base matrix that you can do, NR1124, that's possible. Okay, so this is with BG1. You can do a similar sort of setup for BG2. I'll quickly write that down without showing you all the pictures. So if you do BG2, then you remember BG2 is 42 by 52. Okay, so your K becomes 10 times Z, and your code word bits transmitted is 20 times Z, okay, which means total number of code word bits generated is 22 into Z. Okay, so that's the logic for getting rate half. And now if this has to be roughly 1024, then Z is about 52, I think some 50 odd something you'll get. Okay, so if you go back and look at the list of possible things for NR2, you get something around 56, I think. So there is this 56, this comes here. Okay, so you can pick 2, 3, 56 if you like. Okay, or maybe something else also. Let me see, what did I pick? Yeah, so there's also this 2, 6, 52 you can pick. I think this is better. 2, 6, 52 is closer. Okay, so this is something that one can pick from the possibilities. And again, rate is going to be half. You have to take one part of the parity check matrix and decode. Okay, so let me show you how the MATLAB code works out, just to show you one possible case here. This is the LDPC part. Okay, we'll come to the polar part later on. So you can see that I'm taking in I'm reading NR2652, that is the base matrix, and Z becomes 52. Okay, and then you can see I'm setting rate as half. Okay, and then this gives you just the NBRM, which is the part of the total number of code word bits generated. Okay, so this is divided by rate plus 2, the additional 2 that you do for the puncturing, and then you reduce the parity check matrix to NBRM minus KB, only that much you take. But then when you do sigma calculation, you have to be very careful. Remember, K is the rate, actual rate is not is K by N minus 2Z. Okay, so actual number of message bits divided by number of code word bits transmitted. So this N minus 2Z is quite important. I'm taking N to be the total length. So N minus 2Z is the actual rate that you're going to use. Okay, and then after that things continue as it is. There's no big change here. Okay, so maximum iterations will take us 20. It's not too bad a number for comparison. So if you go to list decoding, so I've done similar setup here. I put A as 500, the CRC length is 11. I have a polynomial here. This is taken from the 5G standard itself. And the one parameter here is list size. You can vary this. 4 is something you can consider. 8 also is something that one might want to consider. Okay. Then of course you also have these quantization parameters. So you can put 3 here and 31 here. This is 6 bits with between minus 4 to 4. And if you look at the LDPC case, in the LDPC case I would put R max is 3 and max QR is 31. So I'm taking minus 3 to 3 and the 6-bit quantization. Okay, so these are all choices. So one can imagine there's lots of optimization here over how you do the quantization, how many iterations you do, what is the list size, etc., etc. So one needs to compare and be happy about what we are doing. Okay, so once you decide on these parameters, what do you do? There's also SCD code. There's nothing, no major other choice here other than quantization. So one can do that also. Okay, so this is something that's done. Okay, Now, a quick word about simulations. When you start simulating, you need enough errors. Okay, so here are some simulation results. I've already done some simulations here, and I've compiled the simulation results. And you can see here, this is another MATLAB file where I like to keep all my simulation results. So if you remember, what comes out at the end of the simulation, what we are printing is EB over N naught, FER simulated, BER simulated, number of block errors, number of bit errors, number of blocks. Okay, so this is what we print at the end of the simulation. So we get that. Those values I collect and put them into a matrix like this. Okay, so for instance, if you want to see what happens here, this is let me do for a small SNR, like one which was only 100 blocks. This will finish a little faster. So if you do that, if you go change this to 1 dB, and then the number of blocks near is 100, and then I can go ahead and run. But you will see, notice one small change here. So I am doing this par for. This is parallel for loop. If you have the parallel computing toolbox of MATLAB, this is very useful. This makes this whole for loop run in multiple threads with different values. Okay, so there are some conditions under which parallelization is possible. Mostly it will work. I mean, just put more variables inside the loop if you are not getting things to work, and it will work. And this will run as many times as how many ever parallel processors you have. It will work very fast. So par is a good thing to do. So speed up my simulation. So let's run this for 1 dB EB over N naught, and so it will start the parallel pool. It will take a little bit of time, but you can run this and it will work reasonably fast, and you will get the answer. So this is the NR BG2 case, and you can see how I've taken those values and put them here. Okay, so just to continue with what the simulation results is, the first block is for BG1 and Z equals 24, rate half, R max 3. And the next array that I have here is 2, 6, 52. Okay, again 20 iterations, R max is 3, rate half, and 2, 6, 52. Okay, so these both of them will have something similar. So let's do format short G. Okay, maybe we can run this again. It ran pretty fast, so we'll run it again to get the answers that we want. So I'm expecting something of this sort. Okay, so from the simulation run, let's see if we get that. Yeah, there you go. So it's 0.44. That's pretty close enough. 0.38, 0.44. You'll see in the plot it won't make too much of a difference. Okay. So similarly, one can run the list decoder. So you have the successive cancellation decoder for polar codes. I've run that and I've collected different values. So now a few comments on how I choose these values. So for 1 dB, it's a low enough SNR. I'll run for only 100 blocks. Okay. So I get enough errors. I get some 78 errors. I'm okay. Okay. So if you go to 1.5 dB, I'm running for 1000 blocks. Okay, only then I'll get some 400 odd errors. Okay, otherwise I can't rely on the errors. So remember, number of block errors needs to be of the order of 40, 50, at least 60 or so to have some confidence in that value. Otherwise, I mean, if it's going to be very low, you have to worry about mean, standard deviation, this, that, all sorts of statistics enter the picture. So to get rid of all that, you run long enough so that you get enough errors, and then you don't have to worry too much about being inaccurate. Okay. And so likewise for 2 dB, you have to go to 5000. I've gone to 5000, which gave me about 500 errors, which is very, very good. For 2.5 dB, again ran for 5000, I got 88 errors. And at 3 dB, I ran 20,000 blocks and I got 52 errors. So that's good. So number of block errors is significant. So these values are correct. So you'll see similarly for other cases also, I've run multiple EB over N naughts and different block sizes to get enough errors. So now this is very important. So you might wonder, how do you choose which EB over N naught to run from? It's trial and error. You keep trying with 100 blocks. You keep trying from some 3 dB or so and keep reducing till you get some errors. Okay, and then you slowly increase. Okay, so that's the idea. So you do trial and error. You'll quickly get it, or if you have some idea on how the performance will be, you can start at that point. Okay, so for the successive cancellation list decoding, I've done 2 cases. Okay, so the first case is NL equals 4, number of list size is 4. The other case is list size is 8. Okay, so again I've done simulation for different SNRs and I've plotted. Okay, and I've gathered all the results together. Okay, so I'm not showing you more simulation runs, but this is how I do and calculate. I simulate, gather the data, and put them all into one file. So nice thing, once you put them all into as arrays in one file, okay, I've collected them as arrays in one file, is you can start plotting. Okay, and for plotting, this is a typical command that I've used. Okay, so maybe I'll take this command here, res4, so that you can associate with the matrix here. So I like to use the semi-log y. Okay, so semi-log y keeps the x-axis in linear scale. Remember, the x-axis is already in EB over N0. Okay, it's going to be EB over N0. So while it's logarithmic in some sense, but it's only linear in EB over N0. So 1, 1.5, 1.752, you want it to be in linear scale, and then the y-axis you want to put in log scale. Okay, so semi-log y is a nice command to use, and you can see I'm taking the array res4 of colon comma 1, which is the first column of res4, and res4 of colon comma 2, which is the second column of res4. Okay, so I'm plotting the first column versus the second column. Okay, and there are some parameters here. I'm arranging for what type of line there should be, what type of marker should be, what color should it be. K is actually black, plus means plus marker will come, and then dash means continuous solid line. Okay, and then I pick these line widths because MATLAB's default line widths and markers is way too small. So I like to keep a larger line width and a larger marker size so that the plot comes out quite well. And you'll see here also I've turned hold on. So hold on makes all the plots appear in the same figure. Grid on gives you the grid, and then I'll set a lot of properties. Mostly this has got to do with making the fonts bigger. Again, MATLAB's default font is very small, so I like to make it bigger, then setting the axis and all that. Okay, so let's run this. So we've done all the simulations. When you want to plot, you don't have to redo the simulations. The data is there, and you can ready-made get the answer. Okay, so I think something very bad happened there. So let me run it. Okay, so there comes the plot. So let me make it bigger for you. So you can see the plot here. So I've put a heading LDPC and polar codes. Rate is roughly half, around half. Length is about 1024. I'm plotting the frame error rate versus EB over N0. You can also plot the bit error rate, but frame error rate is quite nice. Okay. On the rightmost side, you have this plot here, and that is the polar code. Okay, the X mark is coming here. The polar code successive cancellation decoder. Okay, so you can see polar code successive cancellation decoder, and that is the plot here. So this is. Let me see if it will let me write anything here. Okay, so it's not letting me write. So I can't show you what this is, but you can see what it is, right? So this X mark on the rightmost is the polar code with successive cancellation, and it's the poorest among all of them. It is on the rightmost. Okay, so at 3 dB only it comes to around 10 power minus 3 frame error rate. Okay, so 10 power minus 3 frame error rate is a good target to have for simulations. It's not too bad. So if you do polar code with successive cancellation decoding list 4, you improve significantly. Okay, so this star sort of plot mark is that one. You improve significantly around 2.1 dB or so, you're getting 10 power minus 3. And if you increase the list size to 8, which is the plus mark here, it becomes more to the left, and it's pretty good at that point. Okay. Also shown is the LDPC with base graph 1 and LDPC with base graph 2, and these are also quite comparable at that block length, maybe slightly to the left of polar, but this has got to do maybe with choice of parameters, quantization, this, that. I mean, so it's not really that much of a difference here. It's within a fraction of a dB. Okay, so you see the polar code and the LDPC code are pretty good at this comparable block lengths, and they are quite nice when you quantize them and simulate, etc. It works quite well. Okay, so this is a typical picture that. I mean, if you were to write a paper about error control codes or write a report, you have to include a plot like this. Okay, so you take the different codes you want to compare, make them sort of comparable, then run the decoders, calculate the simulation, collect the simulation results together, then make a plot and compare and show how it looks. Okay, so we've done that. So this is what we wanted to do in this code, and to briefly summarize what we wanted to cover as far as this course on LDPC polar codes in 5G is concerned. We wanted to study about LDPC codes and polar codes in the 5G standard. We did that from an implementation point of view, how to get the encoder implemented, how to get the decoder implemented. We wrote MATLAB code for both of those. We did the simulations. Here you go, finally we have compared and we know how these things work. Okay, along the lines you learnt about fixed point decoding, how to implement, how to show the simulations of that, how to do this rate matching a little bit, and quite a few ideas that are there in the 5G standard. So now there are many things we did not do that are in the 5G standard, but we did not do. Okay, so I want to be very clear on that. So you will see, if you go read the standard description, you will see quite a few things we did not do. Particularly in the polar code, there is some interleaving that is needed because of the sequential decoding. if there is a deep fade, the polar code will fail. So, to get over that, there is some interleaving that is needed in the polar code. The LDPC code does not need any interleaving. So, that is one added thing which did not do at all. And for very short block lengths, to help the successive cancellation decoder for the polar code, there is in the standard they add some 1 or 2 parity check bits. Okay, so that part also was not touched upon at all in this. And then also there is, for some cases, interleaving of the CRC bits, so that you can use the early CRCs to direct your sequential decoder in the direction you want. Okay, so all of those things we did not include in our simulations. They are not too difficult. I will encourage you to read those things on your own and think about how you might want to implement them. Okay. Anyway, thanks a lot for staying through in this course till the end, and this is the last lecture, and all the best for your future studies. Thank you very much.